I took the videos out, which is disappointing, but I'll just get through this again. So we're towards the end of the session, so I won't go through the motherhood statements. But this is important work to try and define the backbone of Mount Isa, which is key to understanding mineral deposits in the district. And the key findings of our work are that we've divided the basement into 5 distinct terrains that can be defined beneath the outcropping Mount Isa province. The boundaries of these terrains provide crustal scale zones of weakness that readily reactivate. A thick, resistive, deep-rooted lower crust block termed the Pita Pita Seismic Province forms the core of the Mount Isa inlier, and it has an Archean style signature in its crustal separation ages. The association of conductive anomalies in the broadband MT data indicates the alteration and supports the interpretation. Several of these crustal scale structures act as conduits for fluids and magmas. And the Igneous suture near surface within the Soldier's Crap group versus the Igneous suture at depth marks the eastern limit of the central Isa, whereas juxtaposed against Numal. And so just thought in the spirit of the Olympics, I've put the 5 different crustal blocks, the Tenet, Altuara, Central Isa, Pita Pita, and Numal terrains. So the geological framework of the Mount Isa inlier is complicated and has been well published on for hundreds of years, or at least 100 years. And Karen has covered it off quite well, but basically there's the core of the Mount Isa inlier at surface is the Kalkdoon-Leichhardt belt and some cryptic outcrop of pre-1870 rocks, which you see at depth that are much more extensive. And then there's the superbasin sequences which overlay these, which are controlled by the basement architecture to some degree. And there's also cratonized through at least two or 3 major granitic intrusion events. Firstly, the Kalkadoon-Leichhardt event, and then the Wonga Burstal, and then the Williams Sweep. So we took all this geology and divided it into 23 different units, which we've used to support the seismic and the gravity interpretation. So this is how we've divided all of the sequences. So there's it's a sort of hybrid division because of what we can actually achieve on the seismic interpretation. There's the basin level divisions, but in the eastern succession there is some unit level divisions, and the lower crust there at sort of seismic province scale. And we've assigned densities to them from published works. I'll go into a little bit more, but tried to assign real or imagined suites of lithologies to them so that we can try and root our interpretations in reality. It's for the gravity modeling, which was a fairly large part of what we did. The approach was to use GMSys and create in Oasis Montage and to create 2D gravity models for each of the seismic sections and ensure we use a consistent density model for all the blocks, which I just showed there. There is some variation within some of the blocks, which I think is acceptable because they do have a range of lithologies in them. But we took care to not exploit this and use it to our advantage. The first thing we did was establish a long wavelength feature fit for each of the models, starting with the interpreted MOHO topography and the lower crustal blocks. And because we did this and used this scale of modeling, we were able to not fit a regional gravity tilt to the models, and we were able to make them all fit the observed data except for CF1. Except for IG1. And we had to apply regional to that because we couldn't continue to make all the other models consistent without doing something on IG1. And it seems to be what was done in the Korsch paper in 2012 as well, because we regenerated that model and we had to put a regional in it. And so all the models were generated from free air gravity data from the Queensland gravity grid at 500 metre spacing, and the MOHO was mostly interpreted by us, but in some sections what we did was to use the Osmoho product, where either we couldn't establish a fit at all, or there was just massive discrepancies between what we were seeing and what they had modeled. So we had used that in some places. And once a reasonable fit was established across the entire network of sections, the surface mapping and solid geology interpretations were used to assist in discretizing the upper crust to enable a better fit for high frequency part of the gravity data. And the aim of the modeling was to not so much generate perfect models that fit, but to ensure that the interpretations could match all the features on the gravity profile adequately. So that's one of the data sets that we use to try and support the model and root it in reality. And the other ones are the Geochronology. So we've collected some samples of uranium lead, and we've also done a little bit of lutetium hafnium work, and we've lent heavily on the existing samarium neodymium Wholerock data from Dave Champion. And basically, I just put this slide in to talk about the geochronology techniques in a little bit of detail, in that the uranium lead zircon dating allows us to directly date the age of crystallization of igneous rocks and also infer the age of deposition of sedimentary rocks and date metamorphism, but it dates the event, and that's usually in the upper or middle crust. Whereas the lutetium hafnium and samarium indium Wholerock techniques allow us to gain information about what's happening in the lower crust, because you're looking at both like the source regions where you're melting the rock and the bulk age of when the rocks were extracted from the mantle. So the way this works, when the rocks are extracted from the mantle due to igneous activity, plumes or subduction zones or formation at new crustal spreading centers, the ratio of samarium, neodymium, and lutetium hafnium is set from the chondritic uniform reservoir or the depleted mantle, which is a known value set at the time. And basically the samarium, neodymium behave, the isotopes of that behave very similarly and are more or less in partnership throughout their entire lives in geological history. And the data from that suite is in granites. That's what Dave James collected. And in the lutetium hafnium is a similar system in that the ratio is set when the rocks are extracted from the mantle reservoir and are locked once they are partitioned into a zircon crystal. So this allows us to have a better idea of what's going on at depth. But first of all, we collected there's an extensive suite of shrimp geochronology we collected for the Mary Kathleen program, which helps support this program a little bit in that we see that there's an expanded suite of basement rocks in the southern part of the Mary Kathleen domain, in terms of including the Birdswell granite and the Plum Mountain gneiss. So that sort of helps to feed the idea that this the central isoterrane is more extensive than we previously thought. And also we collected some samples from Geochronology to support this program. So there's DBNQ10 over here is a sample from the Mount Norna quartzite beneath the Tool Creek volcanics, which is interesting, in the core of an anticline, which is mapped as an anticline on our interpretation. And there's also this DBNQ03, so I'm waiting on screen, is in the western portion adjacent to the Murandangi Burketown fault zone, where we've got the extension of the Leichhardt River fault trough mapped out in the seismic interpretation, and it seems to be the detrital spectra is consistent with that. And then we also tried to date some ancient petroleum holes from out here to the east of the Gidjasucha to get some control and constraint on the basement rocks out here. And they were mapped, they were logged as basement cores, but probably one of them is from a Malunga basin looking sequence, and another one is acid volcanic in the base of the Galilee Basin, which is interesting, but doesn't really help us with our understanding of the basement terrains. And so this is how we move on to our crustal separation ages. So we collected some new lutetium hafnium ages from rocks mostly in the Mericathlene domain. And for the most part, they're consistent with what we're seeing from the Sumerian neodymium that has been historically collected. We've got some new hafnium data on the Birdswell, and they all sort of plot along at around about zero with a little bit of crustal mixing. But it gets interesting once you convert these data to crustal separation ages, so we can start interpreting them and the history and what they're extracted from. So this is just a plot of the Sumerian neodymium crustal separation age and the seismic lines, and you see there's a major step through the middle of the project area, and this has been recognised. And I suppose the Pilgrim Fault has been a smoking gun, but what we think is that it's more related to what's happening in the lower crust and the Gidgee Suture. So you can see this is a cross-section overlaying the seismic line with the map view crustal separation ages. So it's a little bit of a gnarly figure, but I think it illustrates quite well that along the western portion, you've got all these 2.5 GA separation ages that sit directly above this Gidgee Suture. I mean, above the Pitta block and like centralizer domain, whereas on the eastern side of the Gidgee Suture, on the deep part of the Gidgee Suture, where you're sitting above the sort of footwall of it, you've got these 2.2, this group of 2.2 crustal separation ages. So you've got a real mappable difference in the isotopic character and also a process for generating it. This is another version of the same data, but basically it's showing on the left, there's the igneous crustal separation ages. On the right, there's the non-igneous crustal separation ages. So you can see that there's a derivation of, when you've got sedimentary rocks next to older igneous rocks, the sedimentary rocks are formed from those older sedimentary igneous rocks. I just think it's an interesting way to look at the data set, so I put it in because I put the terrain boundaries in and then I overlaid them with the geology of and colored everything up on the same timescale. So you can pick out different units which have a crustal separation age, an isotopic character that's sort of unfamiliar to the sequence that they're in or the block. So you pick out older or younger portions of it that might be sequence boundaries or potentially, hot, younger igneous things. And another supporting data set that we have is the Wholerock Mafic Geochemistry. This is a plot of the cerium-yttrium ratio, which is a sort of a proxy for the how evolved the mafic rocks are versus, and it's just plotted over the top of a cross section along M6. There's quite a lot of data. Oh, that's 94, sorry. And there's a lot of data down there. And it basically just shows you that in the Soldier's Cap group, you've got these very low cerium-yttrium ratios compared to the western portion where you've got very high cerium-yttrium ratios, and you can effectively map out where there's been, basically where there is thinner crust. So where you've got, well, at time of generation, I guess. I'll get onto that on the next slide. But, so that's the cerium-yttrium ratios again. And you see them in the Soldier's Cap group and the Crudal-Selwyn domain, even parts of the Mericathlene domain, which seems to be somewhat transitional. You've got these low cerium-yttrium ratios, and they're plotted on this graph of immobile elements. They plot down towards this Earmore field, whereas when you look at all these more evolved higher serum ratio ones, they plot up towards the continental arc field. And George Gibson has sort of published on that and suggested that he included the Georgetown data, which plots down in actually in the EMOR field, but uses that as a proxy for crustal contamination for the Mafic rocks. So basically the ones that are closer to this EMOR field and also the ones that have got the low serum yttrium ratios have lower pressure, higher, like more melting, and so they don't have partitioning of heavy rare earths, which indicates there's garnet crystallizing in the source regions, which is indicating higher pressure conditions in these continental arc rocks, and shows that there's a significant change in magmatism from east to west, which fits in with the model that Karen showed us earlier. That's all I really wanted to show today. It's just that there is some data sets that we've collected that are complementary to this work that we've presented today. And yeah, thanks.